further look into another important chart, you guys can look at these definitions uh, later, but let's look at this chart. What this chart is trying to explain, that what is biasness, what is variance. Okay, so first of all, guys, you should know that both bias and variance are kind of errors of the model. Okay, so what this screen is explaining is, on the x-axis I am having the complexity of the model, on the y-axis I am having the error of the model. So what this means is, if I move from one model to another, let's say model 1, model 2, model 3, and so on, and I am trying to increase the complexity of the model. So let's say this was the simplest model, a linear regression model. Then I move to, let's say, ridge regression, lasso regression, or maybe I move till deep learning, neural networks. My model complexity is increasing, right? Let's say there is decision tree, and then there is random forest, which is even more complex. Decision tree is simple,
Mm.
random forest is complex. So when we are moving from simple to complex model, how the error behaves. So normally, if you look at this green, it is talking about the biasness of the model, guys. So biasness normally decreases as you move towards the complex models. That's what I was telling you above. If you have an underfit scenario, you will try to move to a better model, a more complex model, right? So that the biasness decrease, because complex models stops doing assumptions. Simple models works on certain assumptions, due to which they tend to underfit. So, but the complex models, they don't assume things, means they don't have biasness. Okay, but the problem will come as you move towards the complex model. The variance keeps increasing, guys. Because what is variance? Variance is that on, let's say you have training data 1 and training data 2. So you have two data sets. So let's say Deepak is using training data T1 and Anup is using training data T2, but they are using same model, both of them. Okay. Now, ideally, if both of them are using same model, so their model should be giving you similar performances if it's a good model. But if we say, oh, this model is giving completely different equation, or the parameter values, this is giving completely different. This model is giving you very high accuracy, this is giving you low accuracy. Means models are trying to overfit on the training data, right? This model might have overfit on this training data, but on this data, this model was not able to perform good. So ultimately, it was not the model which was good, rather the data based on which it was able to give you good prediction. So that is not a good model. It is not a generic model. It's a very specific model, specific to the training data. So what is variance? As you vary the training data, the model will vary. That is variance. So that is also bad. Means a model is varying. Definitely models vary, but they should not vary by very huge amount. That here I am getting 99% accuracy with this data, but on the same model, if I use this training data, I get 50% accuracy. That is not acceptable. Means then something is wrong with the model. It is overfitting to the data. So that is what is variance. The variations in the training data leads to changes in the model behavior is variance. So both of these are bad. Doing assumptions is bad. Showing variance is bad, right? So ultimately, we move towards a complex model. Complex models tries to learn as much as from the given data, and that's where they tends to overfit. So now it's not that simple models are bad. It's not that complex models are good. We always has to look at a sweet spot, something which is in between. Otherwise, the entire world will be using the complex models. That's not the case. What have been identified in the field of computer science for machine learning is that there is always a sweet spot, that as we move towards more and more complex model, we come at an intersection point between these two variance and bias curve, which is the sweet spot where we will say that that's the optimal model. Because ultimately this black line that you see here, guys, it's an aggregated output of these two errors. Means if I take this error and this error for a given model, the aggregated average value is this one. Okay.
Mm.
So ultimately this is the total error. So we need a sweet spot where we have a balance of variance and balance of bias. And that is this point where the total error is least. So our model should always be the one where there is low variance and low bias. Okay. So if you look at the above, I am not saying no bias, no variance. No, guys, that is not possible. So I hope you are getting my point, guys, that every model will always have some bias and some variance. We cannot say no, because then it is that 100% accurate model. We cannot have a 100% accurate model. It will be 99%, maybe 99.5. And guys, remember, in the field of computer science, there is something known as a bias variance trade-off. Means if you try to decrease the bias, variance will increase. If you try to decrease the variance, biasness of the model will increase. So we always has to do a trade-off, that what is our sweet point in the given model where I can expect slight bias and slight variance. And that's where I told you that this model can be a good model, because neither the training accuracy is too low, nor there is too much difference between the train and the test accuracy. 5% difference is fine. Now, I hope you guys will be able to understand and explain to your stakeholders that is an underfit or overfit model, whether there is variance or biasness in the model. Okay. So if someone give me this model and another person give me this model, I will always prefer this model over this, because it's not the 90% train accuracy that you should fall for. You should look at the unseen data. Model is not behaving good on it, but here at least more than 70% accuracy in both the cases, and no, not much difference.